I am going to do my absolute doggondest, but I am used to our classes ending like 8 minutes after instead of 7 minutes before. So if we start getting close to 53 and I don't look like I'm going to shut up, someone please tell me to shut up, but in a really nice, respectful way, so I don't have to do anything about it. Also, I do not. I don't have my cool like multi-screen setup as I normally do. So I just need your guys's. If you guys have a question, I'm trying to look on my phone for hands up, but just interrupt me. It's always fine to interrupt me, but more so today because I may not see it right away. Okay. Quick admin stuff. Uh, we have class today, and then we are not seeing each other again till Monday, and it's just Monday, Wednesday next week because we have a 3-day weekend again next week. Don't forget, homework's 14:15 and Lab 5 due next Wednesday. On a personal admin note, I recognize that I have been a horrible teacher and have not gotten you guys your Lab 4s back. That's just between weather, the GR, and having to juggle a little bit of the instructor and course director duties lately. I haven't gotten back, so I apologize. I am working on that, and I will get them back to you before Lab 5. If you have a burning question about Lab 4, let me know. I will happily talk to you one-on-one, but at a minimum, what I'm going to try to get out today or tomorrow morning is a kind of general list of, hey, here is a general list of comments I saw going into Lab 4 so that if there's any big things that you guys know about them before you make the same mistakes on Lab 5. So I apologize. Also, I need to get you guys' stuff into Q2I. I keep meaning to do that while I am at campus. It is very difficult to do on a VPN from home. And apparently, God has decided that yesterday and today was not the day either, because as I was doing that, the snow came in, and I decided it was more important that I get back to my house so that if I get snowed in like I did, that it's with my family and not living at USAFA. Nothing against living at USAFA. I'm sure it is super fun and great for you guys who actually have dorm rooms. But my office is, I've not set up a hammock or a cot or emergency rations in my office yet, so I decided to come home. Okay, that's all I've got on admin. Anyone have any admin questions about anything that I am forgetting that I need to add to my to-do list? Awesome. Okay, so I had, what was, other question. I left you guys yesterday. We introduced this idea of the sampling distribution, and I asked you to go ahead and look into the homework of 14:15, the guided lessons, and start looking into the lab and think about what we said yesterday. And bring any questions that you guys had. It's all right if you don't, but does anything have that we talked about yesterday that remains unclear that you'd like to see another example of, or something from the homework or the lab that doesn't sit right or jive with what we have said so far? Awesome. Okay, I'm going to assume that that utter silence is not that you guys all slept in and are still groggy. I'm going to assume it's because I am an amazing instructor and you guys have no questions and you understand what's going on. That said, if that changes at some point, interrupt me and let me know. So, as a reminder, yesterday we introduced this idea of a sampling distribution. And like I said, this is it's a very kind of conceptual thing, but it is going to be very important for what we are doing. So I really want to make sure you guys understand it. If there is something on here that is you're not understanding, rather than saying, oh, I'm sure I'll figure it out next week, ask me now because I've got the time now to do it. But the idea of the sampling distribution, right, was that if I have an actual parameter of a population, right, in this case that I know 52% of the population is men, if I take a sample of the population and estimate that parameter with a point estimate p hat, and I do that over and over and over again, and I go ahead and look at this distribution of how frequently I get different estimates, what we said is that that is called the sampling distribution. And it is not that I actually ever make a sampling distribution. It is just important that I know that if I were to take those samples over and over again, that the sampling distribution would look like this, right? It would look normal, and that it would be centered around that the expected value of that distribution would be the actual parameter, right? And this is what leads us to the central limit theorem, right? The central limit theorem says when the observations are independent and the sample size is sufficiently large, the sample proportion p hat, that's our estimate, right, will tend to follow a normal distribution with these following means and standard error, right? Basically, it means here's that sampling distribution. If I keep taking samples and I get another estimate and another estimate and another estimate, and I do that an infinite number of times, that this will slowly converge to this, right? It will, those estimates, right, p hat, which is my estimate of the actual parameter p, those estimates will be distributed according to a normal distribution where the mean of that normal distribution, this where it's centered about, is the actual parameter, and the standard deviation, or what we're going to call the standard error, is this whole square root of p times 1 minus p over n, right? And so this is to kind of skip to the end, the big ta-da moment here is that the central limit theorem tells me that yes, my estimates are not going to be exactly the same as the real parameter. However, I know how my estimates are going to be distributed. So when I get an estimate, I can decide how good of an estimate it is. And we're going to talk more later today and even more next week on what I can do specifically mathematically with that. But before we move on a little bit, does this box right here make sense? Is there any questions about what that box means about the distribution of p hat? Okay, so here is the big caveat though, right? Because I'm going to put this to the side for a second. It says up there, the central limit theorem is great, but it says when the observations are independent and the sample size is sufficiently large, right? So we have a couple necessary conditions for the central limit theorem to work. So the central limit theorem is super important and powerful, but before we can use it, we have to prove that in a particular scenario, we are allowed to use it, right? And so there are two main conditions to use the central limit theorem. The observations have to be independent and the sample size is sufficiently large, right? So let's focus on this first one right now. Observations are independent. Now, this is, strangely enough, this is even though this is not a mathematical condition, this is, and maybe because it's not a mathematical condition, this is the one that I think a lot of my cadets in the past have struggled with the most. And I think the other problem is that the term independent, we use several different ways in this class, and it is important to understand the different definitions of it, right? And this is not just an annoying Math 356 thing, right? Context is always important for words, right? If you say, hey, Lieutenant Colonel Richards is tall, that means, hey, my height is taller than everyone else. If you say, hey, his Starbucks drink is a tall, that means that his drink is smaller than everyone else's, ironically, because Starbucks doesn't make any sense. But the point is that context matters, right? So up until this point, we've already talked about independent in two different ways, right? Early on, when we introduced the idea of scatter plots, we kind of alluded to the idea that if we're talking about variables, two variables are independent or dependent if we look at them on the plot, and if there is a relationship between the two of them, like the observations go in a line or maybe in a curve, then we say, hey, those variables are not independent. They are dependent because they depend on each other because there's some type of correlation, right? But that is when we were talking about if two variables are independent or dependent. Then when we were talking about probability, specifically in Lab 3, we said, what if we are talking about if two events are independent, right? And in that case, two events being independent meant that the probability of one event happening had no impact on the whether or not another event happened, right? And so that was a mathematical property, right? Because we said if the probability of A is equal to the probability of A given B, meaning that the probability of A does not change if B has happened, then the events A and B are independent, right? So that is when we talked about if two events are independent. Now we are talking about a third type of independence, right? We are saying, are the observations independent, right? And so when we are doing a sample, the observations are what makes up your sample. If I am curious what proportion of USAFA cadets are male, if I take a sample of 100 cadets, then that means I have 100 observations. Each observation is a cadet, right? It's a cadet that I've chosen. If I am looking at an assembly line of Apple iPhones, and I want to know how often this machine makes a mistake, then I am going to take a sample of 1,000 iPhones. And in that case, I have 1,000 iPhones. I have 1,000 observations, and each observation is an iPhone, right? So what an observation is depends on what I am sampling, right? But it is the things that make up my sample. So when I ask, are observations independent? What I really mean is when I choose one observation and I choose another observation, is my choice of observation in some way depending on the other, right? So, sorry, I dropped my pen here. So if I wanted to take a sample of 100 cadets and I put all of your names into a hat and fully shook it up and took out 100 names, that would be an example of observations being independent, because as the second bullet here says, if the observations are from a simple random sample, then they are independent because I chose one name and then I chose another name, and this name, deciding to choose this name, had nothing to do with the choice of this. On the other hand, for example, let's say I am looking for samples and I go to, let's say, Brooke here, and I say, hey, Brooke, I need a sample of 100 cadets. Would you be willing to join my sample? And she says, sure. And I said, great. Could you help me out and see if do you have like 50 friends that you could join? And she says, sure, no problem. Well, then that's no longer an independent sample, right? Because it's quite possible that Brooke has more friends who are women than men, or maybe more friends who are men than women, right? But the rest of the sample depends on her. And so by choosing her, I have now made the rest of my sample dependent on that observation. So the observations are not independent, right? And so that's what it means when we talk about, are the observations independent? And that's why it is a bit of a subjective check. So as you look at this box here, it says, here's how we verify if they're independent. If an experiment, if the subjects in an experiment they're considered independent if they undergo random assignment, right? So if I am trying to do an experiment where I say, hey, I'm going to give some people a drug, some people a placebo, I bring people in, but then I randomly assign them to groups. Okay, then my observations are probably independent. If I am just picking a big sample, but it is a simple random sample, then I can assume that my observations are independent because it's totally randomized. And that last bullet there is basically saying, hey, if the sample comes from a process that seems random, like error on an assembly line, checking for independence is more difficult, right? Maybe there's some confounding variable that I'm picking all these observations off of them and it seems independent, but maybe if I looked deeper into it, every time there's a failure, it was when Jeff went to the bathroom and I didn't realize that every time he left, there was problems, right? And so checking for independence might not be perfect. I just have to use my best judgment, right? So basically, when we check if observations are independent, about 9 times out of 10, you're going to say, hey, look, these observations were taken from a simple random process, therefore they're independent. Anything else, you're going to have to just use your best judgment and either say, hey, it seems like they were taken from a random, or we don't know how, so we're going to assume they are, or they, at very least, if you look at it and it goes, hey, this does not seem like this was independent, then you would still do your experiment, but you would write, these results should be taken with the caveat that there seems like there is a strong possibility that these observations aren't independent because of this, this, and this, right? And that is actually fairly common in the real world, where you do some type of research or experiment and you present your results. What you'd love to say is, and here's why I know that they are independent, because I did all this work to make sure that it was fully randomized. But at a minimum, you say, hey, here's our results. We think they're good, but here's some things where we think there's some indication that these observations might not be independent. So these are, I think, good results, but before you invest $10 billion based on them, you should probably invest at least $1,000 to go investigate if this is truly independent, right? So we either need to show why they're independent or add a caveat of saying, here's why they might not be independent. Any questions on what independence means when we were talking about observations in a sample? Awesome. The second one is actually much easier to talk about because it is just a mathematical statement, right? We're saying, is our sample size sufficiently large? Now, the only reason why this is a little bit harder would be, some people have said, well, can't we just say, how big does our sample size have to be? Is 30 big enough? Is 100? Is 500? And just set a number and say, as long as it's bigger than this, we're okay. But the problem is that depending on what we're trying to test, one sample size might be big enough for one, but not big enough for another experiment or sample, right? It has to be compared to the proportion we are trying to estimate, right? So in the example we had yesterday where we said, hey, the real parameter is that 52% of Colorado is men and 48% of Colorado is women, we might have less issue with that. However, if I said, I'm going to try to estimate the percentage of cadets who say that Math 356 is their absolute favorite class, right? And let's say that the real parameter is 0.01% think it's their favorite class, and 99.99% say it is not their favorite class, right? Well, then it is going to be very hard to get a sample that catches some of those people who like it, right? And so I'm going to need a bigger sample, or I am going to never see any of those great students who think this is their favorite class, right? And so that's why when we look at this condition here, it is comparing n to the parameter p, right? Or to the parameter 1 minus p, right? So we're saying, hey, the size of my sample times the parameter p has to be greater than or equal to 10. And n times 1 minus p also has to be greater than 10, right? So this, in our male female, I'm going to say the proportion of males times my sample size has to be greater than 10, and the proportion of females times the sample size has to be greater than or equal to 10. Or basically, if I say, hey, here's my sample, the proportion of people that meet my success condition times n is greater than 10, and whatever proportion meet the fail condition times n have to be greater than 10, right? That's why this is called the success failure condition, because I am comparing my sample size to the proportion that meet my success condition, and then I am comparing the sample size to the proportion who meet my failure condition. And so that is how we test to see if our sample size is sufficiently large, basically given what the parameter is we are trying to test. If you're curious, I wasn't going to go into it now, but in the book, there's actually a couple pages where it dedicates to saying, well, what if this, why do we care about this? And it shows what happens to the graphs if this condition is not met, why our graphs start to look wonky and not as useful. So any questions about the success failure conditions for sample size and how we test it? Okay. Now, One optional condition that the book brings up, and I'm going to bring up here because I think it comes up in at least one of the homework questions, is there is this optional condition for the central limit theorem that the sample size be less than 10% of the population, which at first you might say, well, that's dumb. Bigger sample sizes are always great, right? And that's true. But we get a couple of estimation issues that it's basically as it starts to get bigger than 10% of our population, we're getting less and less of an estimate and more close to the actual parameter, which is not a bad thing if we just want a good point estimate. But some of our rules about our how our estimates are distributed start to break down when they are above, when the sample size is above 10%. So it is just something of saying, yes, an estimate, a parameter that is, a point estimate based on a sample that is too big is going to be a good estimate. It's just that some of the assumptions about the central limit theorem may not begin to hold perfectly, and you may get answers that are too conservative. So look at the book on that and just be aware, I believe there is a homework question where it talks about which of these violates central limit theorem conditions. And this is definitely, I think, one of the optional conditions that hold on there. It's usually not a problem in the real world because we're not lucky enough to have too big of a sample. We're usually struggling with, is our sample big enough? But it's just something to be aware of. All right, any questions about anything you see on this screen or anything that we were talking about? All right. Well, then let's talk. Let's work our way through an example and talk about it a little bit. So here's an example. There's an energy company, and it is unwilling to invest in solar research unless they feel that a clear majority of the country is already showing interest, right? So they never took my class, so they hire you guys to help them out, and you decide to conduct a poll of 1,000 randomly selected American adults, and you find that 887 of them favor expanding solar energy. How would you interpret these results to the energy company? Now, I realize that this is a relatively kind of open-ended question, and that's on purpose because this week, like I said, we're kind of focusing on understanding what's going on. Next week, there's going to be questions that are, we'll delve into hypothesis testing and confidence intervals, and we will have more specific questions, but I want you to be able to just explore and understand what's going on. So this is by definition a little bit of an open-ended question. So with this, the very first thing that if I was on this team that I would do, actually, I'm not on the team. You guys are on the team. I'm going to be the energy company. So let me ask George, are you online?
Yes, sir. I'm online. Can you hear me?
I can't hear you. So if you were the person who was doing this, before you set up your presentation, what would be the first thing that you would want to check here before you started making any recommendations to the energy company? Based on what we've talked about today.
Would that just be that you have enough people that are willing to participate in the
Sure. You're basically getting to, I want to check my necessary conditions, right? Because what I'd like to do is I'd like to use all of the stuff that we talked about, which means I want to apply the central limit theorem, but I'm not allowed to use that. I mean, it's America, you can use the central limit, but you're not going to use it responsibly, or it's not going to actually work for you unless the conditions are met, right? So we ran an experiment. What we need to do is check, does our experiment meet the conditions for the central limit theorem, right? So the first one is, are our observations independent? So let me ask Brooke. Brooke, are you online?
Yes, sir.
So would you say that in this scenario, our observations are independent?
I believe so.
Okay, do you have what tells you that they're independent besides your sixth sense?
That they're randomly selected.
I agree, right? This line right here. this line right here that says we took a poll of 1,000 randomly selected Americans. So if this was a question that you were, answering in a lab or whatnot, you could simply say, first, let's check the essential limit theorem conditions of our experiment, and you would say, because the sample comes from a simple random process, we can assume they are independent, right? If I, however, took these words out and it just said you decide to conduct a poll of 1,000 American adults, then you would probably be required to say, either something like, assuming that our sample was randomly selected, then these are independent. Or you could say, we're going to move forward. However, we would need to find out how these 1,000 were selected before we could decide whether or not they were independent, right? Some caveat or acknowledgement that either, hey, that's in there, therefore they are independent, or it's not. And so acknowledge that we don't know for certain. So that's all you need on there. Any questions on checking observations or independent? So I agree with our initial surmisal that independence of observation is met. So next question. Is our sample size sufficiently large? So let me ask Jacob, you online?
Yes, sir.
All right, so how would I answer that question? What's your best guess at how we're going to figure that out?
I'm not quite sure. I'm not quite sure how to check that.
And that's totally fine. So we talked about it on the last slide. And the nice thing is this is an open book course, so you're always welcome to go back. So here, we're looking at those success failure conditions, right? So to check if our sample size is sufficiently large, we need to know, is NP greater than or equal to 10, and is N times 1 minus P greater than 10? Now I agree, part of the problem is P is the parameter that we're interested in. We never explicitly defined it. So what do you want to call P in this situation? What do we want to do? Let P be what? So what is P in this situation? Or what do you think it would be useful for it to be?
Is P the percentage that favor expanding solar energy?
Right. So let P be the proportion of Americans who favor, excuse my handwriting, expanding, I don't know why I decided to capitalize that, solar. And I'm like, no. So, but more importantly, I have nothing in there about my sample, right? Because P is the actual parameter. So the thing that the energy company is actually interested in is they want to know how many people in America support expand. Yeah, no one asked you, Siri. They want to know what the actual proportion of the entire population is, right? And so that's what P is. Okay, so that's the parameter that we were interested in. So going back to here, to check if our sample size is sufficiently large, we need to see, is NP greater than or equal to 10, and is N 1 minus P. So I need to say, I need to check this is true, and I need to check that this is true. Right? Okay, so what is N? I'm going to go back to Jacob. What's N in this situation?
N is 1,000.
Right, N is 1,000. That's our sample size, and we polled 1,000 Americans, and so that is our sample size. So then let me ask you this. What is P in this situation? I'm going to warn you, this is a trick question.
Would it be 88.7.
88.7%. So you are absolutely certain that exactly 88.7% of all Americans support expanding solar energy?
Nope.
What's that?
No,
Why aren't you?
because this is just a sample.
Right. So we don't actually know P, right? That's what I'm trying to get at. Because what do we actually have? We know, I agree that we know something is 0.887, but it's not P. What is it?
P hat.
Exactly, right? We have an estimate of P, right? This is a scenario, unlike the Colorado one, where I did not say, hey, I know what the real answer is, but just for funsies, let's estimate it. Here we're saying, I don't know what the real one is, right? And so you took a sample, and so we have an estimate of P, but we do not have the actual P, right? This is actually what happens more often than knowing what the real P is, right? So if I know what the real P is, I would use P in this equation and in this equation. If I had a assumption of what P is, like if the energy company came to me and said, we think that the proportion of Americans who like it are 38%, then I would use that in there. But since we have no real knowledge or assumption, then I am allowed to use P hat as my best estimate. So I am going to cheat and use P hat in here, and I'm going to put 0.887 here, and I'm going to put 0.113 here, right? And this is equal to 887, and this is equal to 113, and both of those are clearly greater than or equal to 10. Sorry, I ran out of space there. And so even though it's just an estimate, I can feel pretty confident that my sample size is sufficiently large. Yes, maybe if I took another sample, I would get a slightly different P hat. And maybe if I got, instead of 887 here, maybe if I got exactly 10, right? Or 10.1, then I would say, whoa, that's just barely big enough. And this was just an estimate. I should probably do some more research before I feel confident that my sample size is sufficiently large. But because I'm comparing 887 and 113 to 10, I feel pretty good that based on my estimate, my sample size is sufficiently large. So we didn't know P, so we estimated it with P hat to check our sample size was sufficiently large, and we see that it is. So does anyone have any questions about how we can say comfortably here that our sample size is in fact sufficiently large? You guys feel pretty good about that? Any questions?
Wait, I do have a quick question.
Yeah, do it.
So if so the only way that this would even work is we have to make sure that it's randomly selected, right? Because I feel like if it was not as random and we just seem to have a cluster in one area or something like that, then the numbers would be completely arbitrary.
Exactly, and that's why this first condition we had to check that it was met, right? That the observations are independent, because the observations being independent means that they were completely randomly selected, right? But you're exactly right. If I went to a place where, let's say I was in the, I got my random sample near the oil fields of Texas, then I am probably going to get I'm going to get an estimate of people who expanding solar power that is not representative of the entire country, right? And so that's why that first condition is so important to say, are my observations independent? Can I say that this was truly a completely random sample, right?
Thank you.
Definitely. Okay, so we've got they're independent, and we've decided that our sample size is sufficiently large. Okay, now next thing we're going to do is we're going to calculate our statistics, right? Now, we already actually cheated, and because we needed to use P hat to estimate P, we already calculated p hat and said that was 0.887. But again, if I was writing this as an answer to a lab or an actual report to an energy company, saying that p hat equals 0.887 only makes sense because I defined p, right? I said, let p be the actual proportion of Americans who support expanding solar energy. Based on that definition, p hat, or the estimate of p, is 0.887. Okay, so define, unless it's already said, you know, hey, they want to find this, I need to say what p is before p hat has any meaning, right? The next thing I'm going to calculate is the standard error of p hat. So let me ask Allie, are you online? I got too many Alexanders in my class. I forget. Do you go by Alex or Allie? Or Alexandra?
I go by Lexi, sir.
Alexi, okay. I'm sorry. I literally have 3 Alexanders now. With teaching the other M-Day classes, I counted the other day. I am literally teaching over 50% of the Math 356 students, so I apologize. My brain can only hold so much information. I've already gone out of my way to forget my children's names and birthdays to try to make more space for you guys, but it's just not enough. So, Alexi, the standard error of p hat, do you have any memory of how to calculate that?
No, sir, I don't.
That's all right. I honestly, 50% of the time, do not myself. But again, this is a open book class, so we can just go back and say, there it is right there, right? And that is also in your book, right? So that is the standard error of p hat, right? So I'm going to go back over here, and I'm going to say the standard error of p hat equals the square root of p times 1 minus p all over n. Okay, so now let's start filling it in. What is, so I'm going to stay with you, Alexi. What is p?
P is the 0.887.
Ooh, trick question. That's not what p is. What is 0.887? Says right over here, what is 0.887 equal to?
It's p hat.
Right. Now, I do agree with you that we don't know p, so just like before, it is okay if we estimate it here with p hat, right? So I know I'm being a bit of a stickler here, but this is the type of thing that it's going to be important that you understand and differentiate, right? So this is the actual standard error if we knew p, or we had an assumption of what p is. But we don't, so we have to use an estimate, but that's okay. But we have to acknowledge that that's what we're doing. We're estimating it. So I agree that we should definitely put in 0.887 here, and we should put in 0.113 here. But we have to acknowledge that that's not p, that's p hat, and that we're doing an estimate. You good with that?
Yes, sir.
All right, so then let me ask you, and then what is our denominator? What is our n?
That's the sample size, so 1,000.
1,000. And I realize that's not a hard question, but I've had people say 887 before, and so I just want to make sure you guys understand the sample size is everyone there. And then I'm not going to embarrass myself and try to do public math. So let's bring up the calculator, and we're going to say 0.887 times 0.113, and then we're going to divide all of that by 1,000, and then we are going to take the square root of all that, and we get about 0.01. So I'm going to come back to here, and I'm going to say that equals 0.01, right? And so that is my standard error. Okay, so now we know our p hat is 0.887, and our standard error of p hat is 0.01. So I'm going to, so first of all, does anyone have any questions about how we calculated the standard error over here. We used the equation and then we estimated P with P hat to get our standard error. Any questions about how that worked out?
Yeah, sir. One quick question.
Yeah.
So you only know that value for P hat after you've taken your sample, or
Correct.
after you've done your observations.
Yes.
So, and I don't know if this is necessarily an issue, but at any point, did you substitute in P hat for P when you're trying to like predict what's going to happen, or is this kind of all after the fact calculations?
So if I understand your question correctly, this is a bit after the fact. So for example, a question that came up last section, and I don't know if this is what you're getting at, is saying, well, if I want to decide if my sample size is sufficiently large, I have to take my sample first and then compare it to P hat, and only then do I know if my sample size is sufficiently large. And if it's not, it's too late because I've already done my sample, right? And so it is, and so you might say, hey, is this NP and N times 1 minus P greater than 10 conditions going to be met? And so you're right, that can be an issue sometimes. And so it is, if you're talking about a truly expensive, talking about the real world in a truly like expensive survey or sample, it's not completely uncommon to say, all right, we're going to do a sample of maybe 1,000 or 100,000 or maybe even 1 million people if this is like a worldwide thing. However, before we invest this million, we want to check some of our conditions before we do it. And so they will maybe do what is like a pilot survey, maybe a much smaller, say, hey, we're going to only do 1,000 people to begin with, and we're going to check our conditions like independence and our percentages based on that, and say, hey, if the 1,000 person sample looks relatively good and it meets the conditions and my estimate seems reasonable, then I will do the full survey of 1 million people to get a more accurate number. But I don't want to invest all that money until I work the kinks out, so to speak, in a smaller survey. So that is not completely uncommon, but you are right that we didn't know these estimates and numbers until after we had actually done the entire sample and experiment, if that's what you're asking.
Okay, yes, sir, that answers my question. And I guess sort of in that case you brought up, so because you're not basing your like plan off of, or like, your business actions off of that preliminary survey, you don't really care if you have a sufficient sample size. You're just trying to get a rough estimate.
Exactly. And I'll show you here in a second as we finish this out. Even though we don't have perfect knowledge, which again, most of the time we don't have perfect knowledge. That's the whole point of statistics. I will show that even with this single estimate and no knowledge, how powerful it can be. And then I will also tell you, as a preview, later this block, we will talk about things like the power of experiments and stuff like that, and what things we can decide ahead of time of saying, if we want our experiment, we can say things, this is going to make less sense until we see it. But if I say, I want my sample to be able to detect this small of a difference, I can then, before I take the sample, say my sample size has to be at least this big if I want to be able to detect this small of a difference. That type of thing we can do ahead of time, and we will definitely get into that as we get later in the block.
Thank you, sir.
All right, excellent. All right, so I'm gonna, I didn't mean to erase that. So let's say we said this is met, and we said that is 0.887, and this is 0.01. Then the last question is basically interpret the results, right? You've taken all of your stuff, you've done your calculations, and now we're going to come to the energy company and make a recommendation. So let me ask Cam, are you online?
Yes, sir.
Oh, okay, yeah, I got too many Cams too. That's great. I was talking to another Cam, but let's go with you. So in this situation, what would you tell the energy company? I'm not even going to tell you how to present, but just in general, you stand up and the energy company says, okay, what do you suggest we do? Because their initial question was, we're not going to invest in solar unless there's a clear majority of the country that shows interest. What's your recommendation to them based on what we have put together so far?
It'd probably be that due to our data that we found with the 887 out of the 1,000 people randomly selected, it shows good data that that people are interested in solar energy and it'd be a good investment.
Yep, I agree, right? So he's saying, like, look, we did not have the time or money to find out how many actual Americans do this, but based on our sample, we are estimating that about 89% of Americans are interested. And so we think you should go forward. Okay, all the guys around the table are nodding their heads. Oh, that sounds good. This sounds good. But then unfortunately, one of them used to be in my class and he asks you, okay, well, you said your estimate is 89%. How confident do you feel in that? How reliable is that estimate? Is that just I know that you can get different estimates. And so why should I, care that you took one estimate and that it was 89%? What would your response, if anything, be to
that? Probably that we have a low standard error. So
I like that, right? Because Cam's hitting on a important thing, right? We calculated this up here, our p hat. That's our estimate, right? But we also calculated this standard error. And we talked about yesterday that what the standard error is it is a measure of how much variability we expect to see between samples, right? So when we were running that R code yesterday, right, we saw that, yes, every time I take a different sample, I am going to get a different estimate, right? But the standard error tells me how much variation I can expect to see in those samples, right? And so since our standard error is 0.01 or about 1%, it's basically saying that I'm expecting to see on average variation around only 1%, right? Not only that, but remember we said the whole point of the central limit theorem is that our estimates, since this follows the conditions or meets the conditions of this central limit theorem, then I can be confident that my estimates are distributed according to a normal distribution where the mean is the actual parameter and the standard deviation is my standard error, right? And so we estimated these here with p hat, and we estimated this p hat. But what this means is that if I were to keep taking estimates, and so I could tell the board, yes, we only took one estimate, but based on our analysis, our sample meets the conditions of the central limit theorem. And so I reasonably expect that any sample I take is going to be normally distributed around 0.87 with a standard deviation of 0.01, right? And that standard deviation means, remember we said before, when we look at normal distributions, we say, hey, about, if I go one standard deviation, or in this case, we're calling it a standard error out, that is about 68% of all, in this case, estimates. So about 68% of any estimate I'll get from any sample is going to be within one standard error. If I go out two standard errors, that is 95% of all possible estimates. And if I go out three standard errors, then I can assume that about 99% of my possibilities are through in there, right? And since my possibilities are estimates, what I'm saying is, if I were to, the central limit theorem tells me that if I keep taking a bunch more samples, that 99% of the time, I am going to get an estimate that is within three standard deviations, right? And since the standard deviation is about 1%, if I assume that this is 89%, then that means three standard deviations below that is going to be 86%. and 3 standard deviations above that is going to be 92%, right? So I am pretty sure that if I were to I only took one sample, but if I took an infinite number of samples, that's 99% of those estimates are going to be between 86 and 92%. And I acknowledge I am fudging a little bit of the math here, and we're going to go into the specifics next week, but this is the general idea and why the central limit theorem is powerful. Yes, I only took one estimate, but because I know how the estimates will act in the long run, I can tell them, yes, I don't know the exact percentage of Americans who favor expanding solar energy, but I am very confident that the percentage is somewhere, the real percentage is somewhere between 86 and 92%, right? So unless you were going to make a decision based on it had to be exactly 87%, if 86 is good enough for you, or who cares, if 80% is good enough for you, then I am very confident that the actual number is somewhere above there, right? And so this is the power of it. I only took one sample and I don't know anything about the real value, but based on that, my statistical analysis still allows me to make a very confident inference about where the real parameter P is. And that's where we're going, right? That's the whole power of the central limit theorem and statistical analysis, is that based on an estimate and the knowledge that it meets the conditions for the central limit theorem, I can make these inferences with great confidence. Okay, we're just about the end here. Does anyone have any like last minute questions or things for me to think on for my next lesson about this kind of ta-da moment here of how I interpreted these results and why I'm allowed to say these things? Okay, like I said before, we're gonna see each other next Monday. Spend that time looking at the homework in the labs and go back over the guided lessons if it didn't make sense the first time what I said today. And if you still got questions, send them to me so I can answer them now. And then if they're good ones that I think other people have, that I can bring them into any examples that I show on Monday. But take the time to make sure you understand this, because if you truly understand this, I guarantee you the next couple of weeks are going to be much easier because they are all based around this. So take the time, ask me the questions. If you're looking for EI, remember I am pretty booked for M days this week and next week, but should have some time on T days. So just schedule that earlier rather than later, and I will try to work that in. Otherwise, we are at time. So I will see you on Monday, if not earlier. Enjoy the weekend, make some snow angels, and spend at least 43 minutes this weekend not thinking about math, and I will see you guys on Monday, if not before then.